Welcome to Daily Papers, the podcast where we break down interesting new research. Today we're looking at a paper that sits at the intersection of two huge fields, artificial intelligence and fundamental physics.
That's right. We're talking about the search for the basic building blocks of the universe, things like dark matter, quarks, and the Higgs boson. It's a field that generates unbelievable amounts of data, so it's a natural place for AI to help out. But that raises a massive question.
Which is?
How much can we trust the AI? If an AI tells us it's found a new particle, do we believe it? That's the question at the heart of this paper, titled, "Are We Ready for AI-Driven Discovery? AI Verification Before the Next Fundamental Physics Breakthrough."
It sounds like a pretty high-stakes question. Claiming a new fundamental particle is a Nobel Prize-level discovery. Getting it wrong would be a huge deal.
Exactly, and to understand why, the authors first explain how these discoveries are even made. It's not like you just look through a telescope and see a new particle. It's all about statistics.
The paper calls this the statistical workflow. You have a giant experiment, like the Large Hadron Collider, which smashes protons together 40 million times a second. That creates a fire hose of raw data.
And from that data, physicists have to find a tiny rare signal buried under a mountain of background noise. The paper uses the example of the Higgs boson. We don't see the Higgs directly. We see the particles it decays into, which leave tracks and energy deposits in a detector. It's like seeing faint ripples in a pond and having to figure out not just what made them, but whether they're even real ripples or just random noise.
And this whole process has major bottlenecks. To know what a real signal should look like, scientists have to run simulations, incredibly complex and slow computer models that recreate these particle collisions. We're talking billions of simulated events, which can take months of computing time.
And this is where AI has been a game changer. Instead of running a slow simulation every single time, you can train a generative AI on the output of those simulations. The AI learns the underlying patterns and can then generate new simulated data thousands or even millions of times faster.
It's not just simulations, right? AI also helps at the very beginning, sorting through those 40 million collisions per second in real time to decide which tiny fraction are interesting enough to save for later analysis. Without AI, we'd be drowning in data.
So AI is making everything faster and more efficient, but that brings us back to the core issue of trust and verification. The paper asks a really interesting question. When is it acceptable for an AI to be wrong?
Which sounds like a trick question. Surely you never want it to be wrong when you're doing science.
You'd think so, but the authors draw a brilliant line between being suboptimal and being systematically biased. Let's say you're using an AI to help summarize the raw data. If the AI isn't perfect, you might lose a bit of information. The paper's analogy would be like using a slightly blurry camera. You can still see what's going on, but your final picture isn't as sharp. Your discovery might be less certain, but the result isn't fundamentally wrong.
Okay, so that's a wrong that's acceptable. What's the unacceptable kind?
The unacceptable kind of wrong is when the AI is part of the final step, the statistical test that decides if you've found something new. If the AI has a hidden bias there, it will lead you to a false conclusion. You might claim you've discovered a new fundamental particle when all the AI found was a weird glitch in the detector or an error in its own simulation.
That's the nightmare scenario.
It is, but the paper points out that even a biased AI can be useful, as long as you know it's biased and you can correct for it. They call this calibration. Imagine using a bathroom scale that you know always reads 5 pounds too high. It's technically wrong, but you can still use it to weigh yourself accurately, as long as you remember to subtract those 5 pounds.
So the real danger isn't that the AI is wrong, but that it's wrong in a way you don't know about and can't correct.
Precisely. And that's why verification is so critical. You have to constantly check the AI's work against well-understood processes and data from your experiment.
The paper also reminds us that AI isn't magic. It has its own fundamental limits. One of them is something called inductive bias.
That sounds technical, but the idea is simple. Every machine learning model has some built-in assumptions to help it learn. A model for images might have an assumption that nearby pixels are related. A model for physics might assume certain laws of symmetry are true. You can't learn from data without some assumptions. The goal is to make sure your assumptions are good ones.
And of course, the most fundamental limit of all is the experiment itself. An AI can't analyze data that was never collected. If your detector has a blind spot, the AI will have that same blind spot. It can't magically recover information that was never recorded.
So, given all this, the power, the pitfalls, the limits, what does this mean for the future of science? The paper talks about the physicist of the future.
And their job sounds quite different. It's less about being in the weeds, crunching the numbers, and more about being the orchestra conductor.
I love that analogy. The physicist's role is shifting. They're the ones who design the experiments, choose the right AI tools for the job, and most importantly, orchestrate the verification process. They're the ones who have to understand the AI's limitations, check its outputs, and translate a statistical blip into a real physical insight.
They are the essential human in the loop, providing the scientific rigor and the critical thinking.
So, to go back to the title, Are We Ready for AI-Driven Discovery?, the paper's answer seems to be a cautious yes, but
Yes, AI is an incredibly powerful and essential tool, but it comes with a huge responsibility.
a responsibility to verify, to validate, and to never blindly trust the output of a black box, especially when the biggest questions about our universe are on the line.
It's the perfect partnership, the brute force computational power of the machine guided by the careful, critical, and curious mind of the scientist.
A great summary of a fascinating paper. That's all the time we have for today on Daily Papers.